Hi, I'm Jason.
I'm Jen. We're presenting the paper, How Do Classifiers Induce Agents to Invest Effort Strategically by John Kleinberg and Manish Raghavan. As a quick roadmap, we'll first go through the motivation behind the paper, the model setup, including how the authors define effort. From there, we'll go through the results. And finally, we'll conclude with the key takeaways. Starting with the motivation, let's consider a decision-making process in which there is an evaluator who is making some judgment about an agent. In a school setting, this might be a student and a teacher, and the teacher is deciding how to assign the student their final score based on a set of features like test scores and homework. And they're doing this to measure the student's effort in studying for the class. They decide to weigh the test score more heavily, let's say, and the student now, knowing that the test scores matter more for their grade, then might decide to cheat. The students might end up with a good grade in this case, even though the teacher did not intend to reward or incentivize cheating. And this is where we run into the Goodhart's law, which states that a proxy measure intended to be a useful indicator can lose its effectiveness once it becomes the goal itself. You can extend this example to many other settings in decision making. And in this paper, Kleinberg and Raghavan set out to address the discrepancy between the metrics used by evaluators and what evaluators truly value. For a classifier to be considered robust in this case, it must be resistant to manipulation or gaming by the agents it is evaluating. And so the question then becomes, how do we design evaluation rules that encourage the right kinds of effort from the evaluator's perspective? So this work bridges two important areas of research. From economics, we have principal agent models, which study how to incentivize these desired behaviors when actions can't be directly observed. And from the computer science side, we have work on strategic classification, which typically assumes all strategic behavior is undesirable. And this paper uniquely considers how to incentivize specific forms of effort through classifier design. Diving into the model, we have an agent with a budget of effort to allocate across different actions. And these actions influence observable features, which are then used by an evaluator to make a decision. And while previous work has been on single feature models, this paper looks at the multi-feature case where single feature results no longer apply. Our first definition is of effort profile, which represents how an agent allocates their effort across M different actions within a given budget constraint of B. Each component of the effort vector corresponds to the amount of effort invested in a specific action, and the total effort invested in all actions should not exceed the allocated budget to ensure efficient resource distribution. We then have an effort graph that illustrates how different actions contribute to the overall performance or scores of an individual. The effort graph is represented by this bipartite graph where actions on the left from x1 to xm are connected to features on the right from f1 to fn. And the evaluator cannot directly observe the agent's effort profile, but instead they observe features derived from the agent's effort profile. The actions and features are then connected by edges with weights alpha ji, where all the way to alpha mn, where m is the number of actions and n is the number of features. And this graph captures how effort on each action contributes to the value of each feature. To make this more concrete mathematically, we now have a vector of features that represent different aspects of the agent's performance based on their efforts. Each feature corresponds to a specific attribute or outcome that is affected by the agent's actions. We have an effort conversion function, little fi, that describes how the efforts invested in each action are translated into changes in the corresponding feature values. And note how the feature function is applied after we sum up the weighted efforts. And this captures how the combined efforts on different actions contribute to a specific feature value. We then have the constraint of budget B, which limits the total amount of effort that the agent can allocate across different actions. And finally, we have a mechanism M, which processes the features to produce H, and that represents the agent's utility. In this paper, the agent's objective is to maximize this continuous utility value. Going on to the key assumptions behind this model. First, each effort conversion function is non-negative, smooth, and weakly concave. This means that they provide diminishing returns as the number of actions increase. Second, that each alpha parameter is non-negative, which means that no kind of effort can reduce a feature value. And finally, agents have perfect information about the evaluator's mechanism, which is M of F, and that implies that they're fully aware of how their efforts translate into feature values. And another assumption in the setup that goes without saying is that the agents behave rationally and they try to optimize their effort allocation given the mechanism. This brings us to our second definition on a monotone mechanism. And what this is saying is that with a monotone mechanism, if an agent has higher values in all features compared to another agent, then the outcome for the agent with higher values should be at least as good as the one with lower values. And this means that an agent's outcome should improve as their feature values increase. The paper also introduces the idea of a linear mechanism, which simply calculates the score H based on the linear combination of features with coefficients beta. And throughout this paper, we'll focus mainly on mechanisms that are linear. To illustrate the use of this model, let's consider a classroom setting where a student can invest effort in cheating on a test. So the action of X1 here, studying, which is X2, or copying homework, which is the action X3. And the teacher observes only the test feature, which is FT, and the homework scores, which is FW. The students' combined effort of 3 times X1 plus 2 times X2 then contributes to the score on the test, which is FT. And their combined effort of 2 times X2 and 3 times X3 contributes to their score on the homework. From these two scores, the teacher then decides on the student's final grade H. And in this case, we will assume that the grading scheme is just a linear combination of H equals beta T times FT plus beta W times FW. So with this setup, we can now move on to the main results. Starting off with a characterization of which effort profiles can be incentivized. We have theorem 3, which states 3 equivalent conditions. First, there exists a linear mechanism that incentivizes the profile. Second, there exists any monotone mechanism that incentivizes the profile. And third, all profiles with the same or smaller support can be incentivized. And importantly, this tells us that linear mechanisms are sufficient. If any mechanism can incentivize a profile, then a linear one can as well. And a quick note on the third condition, it makes an interesting statement about the properties of incentivizability under this model. It suggests that incentivizability is only affected by the set of efforts we're interested in agents putting non-zero effort into, and the specific distribution of effort across the effort profile doesn't matter. We'll see later while going through the math that this result will make more sense when we see that it depends most significantly on the alpha weights of the effort graph. We then have theorem 5, which addresses a scenario where the evaluator tries to incentivize specific effort allocations while maximizing a defined objective function, G. And let's assume that G is concave and let D be the set of effort variables that the agent can invest into. The first statement is then that we can maximize G over the space of effort profiles in polynomial time if there is a specific effort profile X star where the set of effort variables match the designated subset D and X star can be incentivized. Second, when the number of effort variables in subset D is constant, any concave function G can be maximized over the space of effort profiles in polynomial time. And third, optimizing concave functions over effort profiles subject to incentivizability condition can be NP hard. And altogether, this theorem establishes that it is computationally hard to maximize concave objectives in general, but with certain constraints on the number of distinct actions the evaluator is willing to incentivize, maximizing the concave objective is then a more tractable problem. We can write the agent search for an optimal strategy as this optimization objective. So to maximize H, this is how an agent who is aware of M of F would allocate their effort. Optimal solutions will invest all budget because our mechanism is monotone. And note how the optimization problem is formulated as a linear program, which we can solve later on. We also want to address this question of substitutability, which is when a particular form of effort can be exchanged or transferred for other types of effort at a more favorable rate. And this means that investing effort in one activity can lead to improvements in multiple features simultaneously. So if we let EJ be the effort unit for action J, and we currently have an effort profile X star that is beta times EJ, then we can try to redistribute our effort to a new profile Y. And to optimize this transfer, we want to improve our results along 2 dimensions. The first is that the feature values do not decrease when we transfer to Y, which is specified by the constraint alpha transpose times Y is greater than alpha transpose EJ times EJ. And the second is that we want to minimize budget use. And since EJ invests exactly one unit of effort, when kappa J is less than 1, this means that there exists some investment of effort that uses less than 1 unit of effort and has features greater than or equal to EJ. So going back to the student-teacher scenario, let's try to transfer our effort from X to Y in the context of linear program. Here we set J to be equal to 1, and on the left side, we have Y as our candidate for a reallocation effort. We see that this reallocation reduces the testing feature, which would violate the constraints of the linear program despite increasing the homework feature. We don't always need to invest effort in a single action. In this case, where our effort profile Y is distributed across all actions, at least one of our features still decreases when we transition from EJ to Y. And so Y is not a viable candidate in this case. And if we were to solve out the whole linear program, you would see that incentivizing the effort in X1 is doable because kappa is equal, kappa J is equal to 1. Okay. I'm going to do over that slide. Okay. And we don't always need to invest effort in a single action. In this case, where our effort profile y is distributed across all actions, at least one of our features still increases when we transition from EJ to Y, and so Y is not a viable candidate. And if we were to solve out the whole linear program, you would see that incentivizing f for x1 is doable because kappa j is equal to 1. Now that we've gone through an example for some intuition, hopefully this linear program makes more sense. And to build on single effort transferability, let's look at single effort mechanism, which is when the evaluator wants the agent to incentivize effort toward a particular action. And in this case, let Lj be the set of linear mechanisms which incentivize investing all the agent's effort into action J. Lj's definition makes use of a matrix A, whose entry in the jth row and the I column is the derivative of the feature with respect to effort J. So breaking down the condition Lj, which compares the budget efficiency of efforts to the budget efficiency of effort J, we can convert this condition into a comparison between the derivatives, which shows that the effect of xj on h is greater than the effect of xk on h. And we see here that any movement of budget to a different effort would actually cause our outcome to get worse. And this means investing in effort J is a local maximum. The paper goes on to show that the local optimal is a global optimal through some more complex mathematics in this case, but the intuition behind it is that basically the function we are optimizing over is convex because of the assumption that we made about Fi, and our mechanisms are linear. For next steps, it's important that we establish what the dual of a linear program is. The optimal value of the dual of a linear program is equivalent to the optimal value of the primal. And the two linear programs above are duals, or I guess shown here, are duals of each other. And I'll pass it to Jason to go further into details.
Now we can use the notion of dual linear programs to prove that the set of linear mechanisms which incentivize EJ is non-empty when kappa j is 1. The linear program at the top is our original linear program, which defines kappa j, while the second linear program in the third line is an equivalent derived via the math shown in the second line. Because these linear programs are equivalent, their optimal values are also equivalent. Then, if we take the dual of the second linear program, we achieve the third linear program. So this is line 3 to line 4. Since a dual and a primal have the same optimal value, all three of these linear programs have an optimal value of 1 when kappa j is 1. And there's something to notice about this third linear program. The expressions in its optimization objective and first constraint are the same as the right and left-hand sides of Lj's inequality. We'll see that in the next slide. So now we have that there exists a solution such that beta transpose times aj of x star is 1, while big A of x star is less than or equal to 1 at all of its elements. The existence of such a beta due to the linear program immediately then implies that Lj is not empty because this beta fulfills its requirements. Now we can generalize the concepts of single effort incentivization to the multi-effort case. Here we have the measure of effort transferability for a set S of efforts. Let's look at some of the qualitative properties and insights we can gain from this linear program. The best way to look at it is that Y and Z describe distributions of effort. Z describes what we currently have, and Y describes how we can redistribute Z so that we get the same or better features. Kappa S is then the minimum amount of effort or budget needed to replicate the effect of effort invested according to Z. Alpha S in the top right of the linear program is just going to be alpha with all rows not in S zeroed out. This is basically just so that we're only ever looking um, at the distribution of effort over actions we actually care about incentivizing. Generally, we'll just talk about Z as if it doesn't have any non-zero elements outside of S. Now, let's look at what our constraints mean in the context of this intuition we've just talked about. The first constraint says that distributing effort according to Y yields greater values across all features compared to when we distribute it according to X. The second constraint can be used to show that when kappa S is less than 1, there is some Y and Z such that a transfer of effort from Z to Y reduces the amount of budget used while still maintaining the same features or better. The paper describes using this idea to take an effort profile X, where kappa S is less than 1, and define a more optimal effort profile X prime. If you look at the definition of C, it is defined such that it is the maximum number of times we can take Z out of X without making any of the efforts in X negative. Now with the C, we define a new effort profile X in the middle bottom equation, such that it is X, but after we swap effort in Z for effort in Y, C times. Constraint one of the linear program actually ensures that X prime achieves features at least as good as X. Then constraint two is used in the bottom right equation to show that a budget improvement occurs when we make this effort transfer. Now, let's revisit the student-teacher example for a third time for some more intuition. We'll attempt to incentivize putting effort into X1, X3. In other words, S is the set containing 1 and 3. It's evident that S is unfortunately not incentivizable. Each unit of Z, we'll see, contributes 1.5 to the testing feature and 1.5 to the homework feature. But we could instead allocate effort according to Y because each unit of Y also contributes 1.5 to each of the features, but does so using less budget. Thus, if an effort profile is investing effort in both X1 and X3, then a more optimal effort profile can be achieved by moving some of that effort to X2 instead. Similar to the single effort case, we have a set L of X, which contains a set of linear mechanisms such that X is an optimal effort profile. And again, we can take the inequality and transform it into a comparison between the derivatives of H with respect to each effort. We'll refer to the derivative of H with respect to effort I as the efficiency of effort I. With that being said, the inequality at the bottom actually combines two different ideas in a very elegant way. Firstly, it says that the efficiency of efforts we are trying to incentivize must all be greater than or equal to the efficiency of other efforts. Secondly, it says after you do a little bit of math, it turns out that it says that the efficiency of efforts we want to incentivize must all be equal. In other words, the efficiency of efforts being incentivized together cannot exceed each other and must be at least as good as the efficiencies of unincentivized efforts. This then shows that locally X prime is in fact optimal. And again, because of the convexity of our problem, the local optimal here is a global optimal. Now, all we have to do is verify that whenever the transferability of X, kappa S, is 1, L of X is non-empty, as in there exists some linear mechanism to incentivize X. At the top here, we have the original definition of the transferability of S, kappa S. The second and third linear programs are directly equivalent to each other because their first constraints are mathematically equal, while everything else is identical. We'll see a short proof for this on in 2 slides. The second linear program is actually identical to the first, except we are free to choose z as an input parameter rather than optimizing over it. Since every solution to this linear program is a solution to the first, the optimal value of the first linear program, kappa s, must be as good as the optimal value of the second for any input z. This is where we get the inequality kappa s is less than or equal to kappa s of z. Now, there's something else we need to know about kappa s of z. Let's say we have some z we've chosen as the input parameter. We can then choose y equals z as a candidate to solve a linear program. This is a valid solution which fulfills all of the constraints. So then we have that there is some solution where the sum of y's elements is equal to the sum of z's. That gives us this new inequality. Conveniently, if kappa s is 1 and the elements of z add to 1, then kappa s of z must be 1. Keep this fact in your head for now. It'll be useful later. Now, we'll focus on transforming the second linear program into a much useful form. And this begins with the third linear program. Here's the proof for why they're equivalent. This is just some simple inequality manipulation, just multiplying the same amounts on each side. Very simple stuff. And just so that y'all can take another look at these two linear programs to see the equivalence between them. Now we can take that last linear program and take the dual of it to achieve eta of z at the bottom. Finally, we choose to plug in z equals x star over b. Notice that this results in Ada's linear program containing the right and left-hand sides of L of x. But why is this choice of z significant? Notice that the sum of x star over b's elements is 1 by definition of budget. This causes the following inequality to be true. We now have that wherever kappa s is 1, uh, eta of x star over b is also 1. When eta of x star over b is 1, then there exists some beta that fulfills L of x. In other words, if kappa s is 1, L of x is non-empty. Here, S would refer to the support of x star. Now, we've theoretically proven the relationship between the transferability measure kappa S and the existence of incentivizing linear mechanisms for a specific effort profile X. The next step is then to consider the tractability of finding these linear mechanisms. Fortunately, we have polynomial time algorithms for solving linear programs. Since we're able to pose our problem as a linear program, we can then solve it in polynomial time. Yay. And now that we've characterized when specific effort profiles are incentivizable and how to find their incentivizing linear mechanisms, let's talk about finding linear mechanisms that optimize some function of the effort profile, such as, say, the L2 norm of the effort profile. And unfortunately, optimizing over the set of effort profiles on some objective function is sometimes NP hard. This is just how we would mathematically describe optimizing an objective G over X. And D is just some set of efforts chosen by the evaluator. It basically indicates the exact set of efforts that we're allowed to invest in while optimizing, though this is not too important conceptually. Now, this is a diagram of P versus NP in case y'all forgot. As a refresher, if being able to solve A with a certain time complexity implies being able to solve B with the same or better time complexity, then A is at least as hard as B. NP hard problems are at least as hard as all problems in NP, and many, if not all, NP hard problems have, at best, um, exponential time complexity solutions currently. This is an example of an objective that is NP hard to optimize. This is the L0 norm of X, which is equivalent to the number of non-zero elements in the vector X. In other words, we'd want to find a linear mechanism whose optimal effort profile maximizes the number of non-zero efforts. We'll go over a sketch of the proof for why this is NP hard. The sketch of the proof that optimizing the L0 norm of the effort profile is NP hard is as follows. In the maximum independent set problem, you're given a graph G and asked to find a largest independent set of vertices. The maximal set problem is NP hard. We will create an effort graph according to some G such that maximizing the L0 norm on the effort graph is synonymous to finding a largest independent set of G. First, let G be some graph with edge set E and vertex set V. In our effort graph, we create both an effort and a feature for each vertex in V, and we also create an effort but no feature for each edge in E. And for each edge, E, such that it's equal to, such that its vertices are U and V, the alpha weight between the effort XE and the features FU and FV is set to 2. And additionally, the alpha weight between XV and FV for every vertex V is set to 3. Although we'll skip over the proof, it turns out that for any vertex pair V1 and V2, V1, V2 is an edge in G if and only if any support S containing both V1 and V2 is unincentivizable. This means that any S which does not contain both, or any effort profile which does not try to incentivize both vertices of an edge is incentivizable. Therefore, after optimizing for a linear mechanism where the size of S is maximized, we would then be able to retrieve S and pick out the vertices of G whose corresponding efforts are contained in S. This set of vertices would be a maximum independent set. And to go over it all again, because having an algorithm for optimizing over the L0 norm of our effort profile means being able to solve the maximum independent set problem, the optimization of L0 is at least as hard as a maximum independent set problem and is thus NP hard. Now, we'll very loosely explore the properties of the space of linear mechanisms. Basically, we'll look at a phase graph-like diagram showing the viable linear mechanisms for a specific effort graph. Now, consider the following effort graph. Let's try to incentivize efforts 1 and 3. These equations are the restrictions we get on beta as a result when we apply the fact that incentivizable efforts need to have greater efficiency in affecting the outcome than other efforts. If we set beta 1 to 1, the three equations result in this graph. The authors note that unfortunately, our space of linear mechanisms is not necessarily convex, as seen by the top left edge of the region, making it hard in general to optimize objectives over the space of linear mechanisms. Now that we've gone over all of the main content, let's look at some possible further directions of work mentioned in the paper. Firstly, a possible direction to explore is a stochastic action to outcome relationship. Now, this idea arises from the fact that effort invested in action does not always deterministically lead to the same outcome for a feature. Kind of like how studying for a certain amount of time for a test does not always lead to the same score achieved on the test. Now, another direction to explore is having agents with different parameters or alpha weights. In our current model, we assume that either there is a single agent or that all agents share the same action to feature conversion weights, which is very largely not true in the real world. Another direction to explore that is also inspired by the real world is the characterization of suboptimal behavior. Now, a very big assumption in this paper is that um, if we provide agents with the feature to outcome mechanism, then they will behave rationally and optimize for the optimal effort profile. Um, this is not something that can necessarily happen. And finally, another direction to consider is having constraints on the mechanism's output H. For example, right now we have that H is some continuous value that depends on continuous features, but a possible alteration to this is having a threshold so that H becomes some kind of binary classification. Now let's go over everything that we've gone over with this paper. Firstly, the authors crafted a mathematical model of the effort to evaluation pipeline. Secondly, they rigorously characterized when a given effort profile is incentivizable via a linear mechanism. This characterization was based on the idea of being able to transfer effort between different actions at better rates of improvement to the features. In their characterization, they formulate the problem as a set of linear programs, and we have general polynomial time algorithms for solving linear programs. The problem of measuring incentivizability, then finding an incentivizing linear mechanism, can then be done in polynomial time. Finally, we went over possible extensions to this work. Thanks for listening.